All right, we've already done some calculations with graphs with our gas laws. It's now time for us to look at equations with our gas laws. So this won't be hard at all, and it allows us to quickly find different conditions of gases without having to do graphs. So let's look at Boyle's law first. Boyle's law states that pressure varies inversely with volume. So what does that mean? If pressure goes up, volume goes down, and vice versa. And with Boyle's law, temperature is constant. So if you look at, we have a gas of a volume here of 1 liter. Gas molecules are bouncing around. When the volume gets smaller, they bounce around and collide with each other more frequently, causing the pressure to go up. So again, his equation is pressure 1, volume 1 equals pressure 2, volume 2. And this is typical of an indirect proportion. So we look at our question here. Why don't we pretend pressure 2 is not known? So I'll put a question mark next to that. That way I can show you how this equation works. So pressure 1, volume 1 equals pressure 2, volume 2. It's nice to organize your variables like this when you read a question. So I've got pressure 1, volume 1, pressure 2, volume 2. So pressure 1 is 100. I'm going to multiply that by my volume 1 of 1.0 equals, now I'm pretending I don't know pressure 2, so I put pressure 2 there, and I'll multiply that by 0.5. All right, now I need to get pressure 2 all by itself. So I'm going to divide both sides by 0.5. And that'll definitely give me a pressure 2 equal to 200 millimeters of mercury. So again, that's how it works. And notice how the letter T is not in this equation. Why? Because temperature, which is the letter T, is held constant. Therefore, we don't need it in the equation. All right, let's move on then to Charles' law. Charles' law, we hold pressure constant, therefore the letter P will not be in our equation. And volume and temperature vary directly. So what does that mean? If temperature goes up, volume goes up with it. How do we write a direct proportion? Well, it's going to look like this. Volume 1 times temperature 2 equals volume 2 times temperature 1. Okay, this is a direct proportion. You might wonder, so why is a 2 next to the 1 here? It's because this is a direct proportion. So we swapped the sides there. T2 is on this side, T1 is on that side. So look at our condition here. We have a beginning volume of 5, a beginning temperature of 200 Kelvin, and then we have a final volume of 10 and a final temperature of 400. Now notice how our temperatures are already in Kelvin. They have to be in Kelvin. So remember, Kelvin is equal to 273 plus our degrees Celsius. And notice how, again, we organize our variables very carefully so we can see what they are when we read a question. Let's pretend we do not know volume 2. So I'll put a question mark next to volume 2. Okay, so volume 1 is going to be 5 multiplied by temperature 2, which is 400, equals volume 2, which we don't know, so I'll put V2 as my question mark, times temperature 1 of 200. So again, notice how they're flip-flop there. T2 and T1 are opposites. So I'm going to divide both sides by 200 in order to get my answer. And we're going to see that that equals 10. And liters is my units there. So that's how we handle the direct proportion for Charles' law. Next, Guy-Lussac's law. Pressure 1, temperature 2 equals pressure 2, temperature 1. Now this time volume is constant. The letter V stands for volume. Note how that is not in our equation at all. Okay, and let's take a look what we have here. We have pressure 1 of 1 atmosphere. And we have temperature 1 of 200 Kelvin. And then pressure 2 is 2 atmospheres. And our temperature 2 is 400 Kelvin. So let me put a question mark by temperature 2. I'm going to pretend I don't know what temperature 2 is. Notice how my variables are organized into a nice chart here. Okay, so pressure 1 is 1 atmosphere, so I'll put 1 there. My temperature 2 is what I'm solving for, so I'm going to put T2 right there. Equals pressure 2 is 2 atmospheres. Okay, and then 200 Kelvin is my beginning temperature. Once again, notice how I put Kelvin there. You don't need to put units in the equations. I'm just so used to putting my units everywhere. But it's probably best not to put them in the equations at all. Okay, so then I want to solve for T2. So this time I'm going to divide both sides by 1. I guess we don't really need to do that. But let's do it anyway, just so you understand how to use the equations. So temperature 2, we can clearly see, okay, is equal to 400 Kelvin. So there you go. So as temperature increases, the volume can't change. The frequency and the force of collisions is going to go up, okay, for the Guy-Lussac's equation there. For Charles' law, when the temperature goes up, we're letting the volume expand with it. So this is a different situation, of course, when you don't let the volume change. Okay. Now what about the last one? The last one's called the combined gas law. It's going to put all three laws together. So P1 V1 T2 equals P2 V2 T1. So this is in a case where none of the variables stay constant. So if you look at the first one here, P1 V1 equals P2 V2, that's Boyles law. Now look at V1 T2 equals V2 T1, that's Charles' law. And then look at P1 T2 equals P2 T1, that's Guy-Lussac's law. So you see that they're all included in this one. All right, so let's get started with this question. So gas is a pressure initially of 200 torr. Now that's millimeters of mercury. I'm going to, instead of using torr in this question, I'm going to keep our units all the same. So I'm going to cross that off and make that 0.26 atmospheres. We'll deal with conversions of units later. A volume of 300 milliliters and a temperature of 26 degrees Celsius. So I'm going to make myself a chart. Pressure 1 equals 0.26 atmospheres. I will record my units now to make sure I know what I'm doing. My volume 1 is equal to 300 milliliters. And my temperature 1, oh, this time it's in Celsius. I need Kelvin. So I'm going to take 26 plus 273. Okay, and that is going to give me 299 Kelvin. So I'm going to write 299 Kelvin here. There you go. And I put all my units on there just to make sure the question is not going to be tricky at all so that I forget to convert a unit or whatever. Okay, so there we go. The volume is decreased to 0.25 liters. They're trying to be a little tricky here. That is the same as 250 milliliters. I'm not falling for that trick. And the pressure is decreased to 0.60 atmospheres. I already changed that one for you. You don't need to worry about that conversion right now. What will the final temperature be? Okay, so T2 is now going to be my question mark. So now I'm going to put all of my variables in my equation as I see it there. Okay, pressure 1, I'm going to try to fit it all here, is 0.26. Volume 1 is 300. Okay, and temperature 2 is my question mark, so I got a T2 there. That's what I'm going to solve for. That's going to equal, okay, my pressure 2, which is 0.6. I'm going to multiply that by 250. And my last is going to be 299 Kelvin. And notice how I'm not putting any variables in there at all. Okay, because that will definitely get me confused there. Okay, hope you can see it okay there. I kind of squeezed that in there. I need to get T2 by itself. So I need to divide both of these by 0.26 times 300. Now be careful in your calculator, guys, on this. 0.26, okay, times 300. I'm writing it on the right side, how you would put that in your calculator. You must parenthesis 0.26 times 300, close the parenthesis. There's a good chance of causing an error if you don't do it like that. So mathematically, it'll be 0.6 times 250 times 299 divided by, open a parenthesis, 0.26 times 300, close parenthesis, hit equals. And temperature 2 comes out to be 568.1 Kelvin. And always your answer is going to come out as Kelvin when you're using these equations. It's your job to put them in Kelvin though, and first if they give you a Celsius temperature. Okay, that's how you handle the gas laws mathematically. Okay, and that's it for now, and we'll go through more questions at another time. Boom.